In Lecture 3, we'll deal with the topic of integrated rate laws. Recall from the previous lecture that a rate law is simply rate as a function of concentration. We answer questions about how the reaction rate changes as we change the concentration of reactants. And for our generic chemical reaction, the general rate law would be written here. And we recall that M and N and K are determined by experiment, typically by the method of initial rates. Now, instead of following rate as a function of concentration, as we did in this rate law, can we follow concentration as a function of time? And of course, yes, or else we wouldn't be asking the question here. So we want to introduce the topic of integrated rate laws. These show us concentration as a function of time. So this allows us to answer questions such as what concentration of reactant remains after a certain time period, or how much time is required for a reaction to reach a certain target concentration. However, since deriving these integrated rate laws involves some calculus, which we will not do, but because it does, we'll limit ourselves to, first of all, reactions that fit the generic profile of some reactant going to products. Now you might ask, is this kind of useless? Because this seems like an overly simplified reaction, and it might limit ourselves to so few cases that it's not relevant. Well, it turns out that this simple profile covers a surprising number of situations. For example, there are a number of decomposition reactions that fit this profile. One example would be the decomposition of ozone to oxygen that happens in the upper atmosphere. You can see you have one reactant going to some products. It fits this profile, A going to products. Here's another example. Hydrogen peroxide, which you probably have in your medicine cabinet, an aqueous solution of hydrogen peroxide, tends to decompose over time to water and oxygen. Again, this reaction fits the profile of a reactant going to a set of products. There are a number of what you might call processes that fit this profile. Probably the most common would be the disappearance of drug in the body with time. Pharmacologists and doctors refer to the half-life of a drug in a patient. We'll talk about half-life in the second part of this lecture. Another situation that's covered by this generic profile would be the decay of a radioactive isotope. So for example, radioactive iodine 131, which is used to image thyroids in medicine, decomposes to xenon 131 in a beta particle. Again, even if you don't recall or haven't been exposed to reactions involving radioactivity, this process fits this profile, some reactant going to products. The other thing that we're going to limit ourselves to are reactions that are zero order, first order, or second order in our reactant. So for zero order reactions, recall the rate law from the previous lecture would be rate equals K times the reactant concentration to the zero power, so rate would just be equal to the rate constant. A first order reaction would have this form from the previous lecture, and the second order reaction would have this form. Again, integrated rate laws are expressions that allow us to talk about concentration as a function of time. And as we just said on the previous slide, we're going to look at reactions that fit this generic form of some reactant going to products. Well, if the reaction is first order in this reactant, then we would say, as we've said several times, that the rate law would be rate equals K times A to the first power. Now, if we applied some calculus to this, which of course we're not going to show, we could derive one of these integrated rate laws. This would be for the first order process, and it would look like this. Well, let's define what the terms are in here, and I think this will make a little more sense. A0 here is the initial concentration of the reactant. A sub T is the concentration of reactant A at some future time t. So of course t here is time. And K is the rate constant. So why is this an integrated rate law? Because it allows us to monitor concentration of A as a function of time. If the reaction is second order in A, then we would say that rate equals K times A squared. If we applied some calculus to this, the integrated rate law for the second order case would look like this. 1 over the concentration of A at some future time t minus 1 over the initial concentration of A equals K times t. If the reaction was zero order in A, of course, the rate law would be this, and sorry about that. Applying some calculus, the integrated rate law would look like this, where the concentration of A at some future time t minus the initial concentration of A equals minus the rate constant times the time. Well, let's do an example of using an integrated rate law. Consider this reaction where the rate law was found by experiment to be rate equals K times NOBR squared, the square of the reactant concentration, and the rate constant was found to be 0.56 per mole per second at a certain constant temperature. The integrated rate laws allow us to answer the following question. If the initial concentration of this reactant, NOBR, was 0.751 molar, how long would it take for the concentration of this reactant to drop to 0.1 molar? Well, can we use our integrated rate laws or one of them to solve this? Well, first of all, we can use an integrated rate law because the question asks us about concentration and time. The reaction fits our required profile of a reactant going to products. We have a reactant here going to a set of products. The question states that the reaction is second order in the reactant. Therefore, the rate law fits one of our generic cases, rate equals K A squared, where we have the following integrated rate law at the ready. Remember, of course, you don't have to memorize these integrated rate laws because you'll have them available for quizzes and exams, but you do need to recognize, or it helps to recognize, that this is the one for second order. Now, applied to this reaction, we'd have 1 over the concentration of NOBR at some future time t minus 1 over the initial concentration of NOBR equals the rate constant times the time. And from the information given in the question, we know that the initial concentration of NOBR is 0.751, which we substitute in here. Of NOBR at some future time t is 0.1, which we would substitute in here. And so our job is now simply to solve for t, for time. So notice I've put in these values here, 1 over 0.1 molar minus 1 over 0.751 molar equals 0.56 per mole per second times the time. If we take 1 and divide by 0.1, we would get 10. And since this is 1 over molar, the units here would be molar to the minus 1. Similar math for 1 over 0.751, and we get 1.33 per molar. And we would subtract these from each other and get 0.867 per mole equals 0.56 per mole per second times time. And we can simply solve for the time. And if we pay attention to significant figures, we get 15 seconds. So what we're saying is that it would take 15 seconds for the concentration of NOBR to drop from its initial value of 0.751 to a value of 0.1. Now, and that, by the way, would be down to about 13.3% of its initial value. So if we started with 0.751 and ended up with 0.1, 0.1 is 13.3% of what we started with. So we'd say in 15 seconds, the concentration of NOBR drops to 13.3% of its initial value. It's a pretty quick reaction. You might be able to catch it if you were timing it with a stopwatch on your cell phone. If reactions become much faster than this, you'd need special instrumentation to follow it. Here's another example of using an integrated rate law. Suppose the decomposition of a certain insecticide in water at 12 degrees C follows first-order kinetics with a rate constant of K equal to 1.45 years to the minus 1, abbreviated as 1.45 y to the minus 1. This is units for a rate constant that you don't see as often, but it's perfectly legitimate. Now, suppose a quantity of this insecticide is washed into the lake on June 1st, leading to a concentration of 5 times 10 to the minus 7 grams per cubic centimeter. Again, this is an unusual concentration unit, but it's a concentration unit. We have concentration, we have time, we're okay. So this is the initial concentration of the insecticide. Now assume that the temperature of the lake is uniform and stays constant, so there are no effects of temperature variation on the rate. What would be the predicted concentration of insecticide on June 1st of the following year? Well, we can use an integrated rate law here because the question asks us about concentration in time. The reaction, meaning the decomposition of the insecticide, fits our required profile. Some insecticide going to products. We don't know what those products are, doesn't matter. The question states that the reaction or process is first order in insecticide, in concentration of insecticide. Therefore, the rate law fits one of our allowed generic cases, rate equals K times A to the first power, where we have this integrated rate law for a first order reaction. Now applied to this situation, it would be the natural log of the concentration of the insecticide at some future time t minus the natural log of the insecticide concentration initially equals minus 1.45 per year times time. Now from the information given in the question, we know the initial concentration of insecticide is 5 times 10 to the minus 7 grams per cubic centimeter. We know the time is 1 year because we're going from June 1st to June 1st. And now we simply solve for the concentration of insecticide at this future time t. So we have the natural log of the insecticide concentration at some future time t minus the natural log of the starting concentration equals minus 1.45 per year times 1 year. Now this is starting to look complicated, but I really just did a little rearranging here. What I did was I brought this minus ln of the initial concentration over to the other side of the equal sign. So it's now on this side of the equal sign, and there's a plus sign in front of it. Then I multiplied 1.45 times 1, and these units cancel, years and years to the minus 1, so we get minus 1.45 here. And then I took the natural log of this number and got minus 14.51. So now we have a number of minus 15.96, and I seem to have totally ignored the units. We'll deal with that in a second, but let's finish this problem. So what we know now is that the natural log of the insecticide concentration at the time t, which is 1 year, is minus 15.96. So we want to get rid of this natural log, and to do that, we'll take the exponential of both sides. Now I state this here mathematically how we're going to do this, and that's probably not very helpful to a lot of you, so I'll just show you how it's done here. We're going to take e to the ln of the insecticide concentration. In other words, in my calculator, I'll push the e function, e to the x, and for x, I'll put in minus 15.96. If I do that, I get rid of this ln function on this side, and I didn't write this out here, but what we have here is that this number you get doing this math is simply the concentration of the insecticide at some future time t is this, and now suddenly the units have reappeared because it is a concentration. So it's predicted that in 1 year at 12 degrees C, the concentration of the insecticide will decrease from 5 times 10 to the minus 7 grams per cubic centimeter to 1.17 times 10 to the minus 7 grams per cubic centimeter. That is, it drops to about 23% of its initial value. Well, let's make some notes here. This is an example of a question where rate, which is still a change in concentration per unit time, is expressed in units other than molar per second. Here, rate is expressed in grams per cubic centimeter per year. Therefore, the rate constant has units of years to the minus 1. This is still concentration per unit time. You might be wondering why we ignored units when we were doing this math up here. And the reason is that the units involving ratios actually cancel out. And it all looks a little fuzzy here, how I ignored them and then brought them back. But let me try to explain what I mean here. Here's the equation for the first order integrated rate law. You can rewrite this equation in a different form. If you remember something about logarithms, you can say that the logarithm, the ln function of a sub t divided by the ln of a sub 0 is equal to ln of at minus ln of a0. Furthermore, you can say that this expression here equals the ln of the ratio of these two concentrations. So in a sense, the concentration units in this form of the integrated rate law actually cancel. And so at some point, it's not unreasonable to look at numbers without units. The final answer, of course, was a concentration. So of course, we would express it in the concentration unit that's being used. The final thing you might ask about is significant figures here. You'll notice that, and this may be hard to see because the print's kind of small here, but we have the natural log of 5.0 times 10 to the minus 7. And I said the answer to that was minus 14.51. So it appears I have two significant figures here and I have 4 here What gives? Well, those two significant figures should be the number of figures after the decimal point in the result of the logarithm. Now, integrated rate laws, in some limited but surprisingly useful cases, can be used as an alternative to the method of initial rates in discovering if a reaction is first order, second order, or zero order in reactant. Previously, in the previous lecture, we established rate as a function of concentration. Then in this lecture, we took those expressions, we integrated them and came up with integrated rate laws. What we're asking now is, instead of the method of initial rates in the previous lecture, could we use our experience from integrated rate laws to try to see if a reaction in the first place is zero order, first order, or second order? If you go into the lab and monitor a reaction, what you're going to do typically is look at the decrease in reactant concentration as time proceeds. So you're getting data that's concentration as a function of time. And what you can do is take that data and see which case it fits. And that may make absolutely no sense, which is fine. Let's do an example, and I think it'll clarify it. If a rate law is truly first order, if the rate law should be this, the integrated rate law is this. We've established that before. Now, if I take that integrated rate law and I rearrange it so that it's in the form of a straight line, you say, okay, why is this in the form of a straight line? Well, I'll put the equation of a straight line right underneath it, and you can see that it is in the form of a straight line. Y equals mx plus b, where y is the ln of at, m, the slope, is minus k, x is time, and the y-intercept is the natural log of a0. Under this column called graphical analysis, what we're going to say is that if a plot or a graph of the natural log of the concentration of A as time proceeds versus time, in other words, y versus x, is linear, then it must be that that reaction is first order in A, because if it was not, it wouldn't fit this straight line relationship for a first order integrated rate law, and the slope would be minus k. Likewise, if the rate law was truly k times a squared, we know the integrated rate law for that is this. Again, if we rearrange it in the form of a straight line, all I'm doing is bringing 1 over a0 over to the other side, we can say that puts that equation in the form of a straight line. And we would say now, if you made a graph of 1 over at versus time, if that graph was linear, then, or fit a straight line, then we'd say the reaction must be second order in A, and the slope of that line would be equal to the rate constant. If the rate was zero order in A, the integrated rate law is this. The rearranged rate law in the form of a straight line would look like this. And we'd say the reaction is zero order in A if a plot of the concentration of A versus time, y versus x, is linear, and the rate constant, the slope would be equal to minus the rate constant. So on the next few slides, we will look at an example where the concentration of a reactant is measured at several times as a reaction proceeds. We're then going to make 3 graphs or plots in Microsoft Excel. Plot number 1 will be the natural log of A sub t versus time. That's the first order plot because it's we're testing to see if the reaction's first order. The second plot will take the same data, but instead of ln of t versus time, we'll plot 1 over at versus time to test to see if it's second order, whether that's a straight line. And in plot number 3, we'll plot the concentration of A versus time. And again, we can make an educated guess as to whether the reaction is truly first, second, or zero order in reactant A by which of these plots best fits a straight line relationship. Again, we're doing this if we want to avoid using the method of initial rates to find out what the rate law is for a reaction. So let's see what these look like. The reaction we're going to look at is the gas phase decomposition of NO2 going to NO in oxygen. And here's the experimental data. The concentration of NO2 is measured at various times as the reaction proceeds. So initially the concentration is 0.01, after 50 seconds it's 0.00787, and so forth. So this is time, this is concentration. Concentration of NO2 is going down with time. That's good. Now, since this reaction fits the generic form, A going to products, we can use a graphical analysis to see if the reaction is first, second, or zero order in A. Again, we're not using the method of initial rates. We're using plots of integrated rate laws to try to decide whether this reaction is first, second, or zero order in A. So what we've done here is we've taken this data and we've expanded it. So you'll notice the time column is right here. And I've emphasized, of course, that this is time. The concentration of NO2 we've just written in this column here. And recall, to make these plots, we're going to need more than just the concentration of NO2, the concentration of A at these various times. We're going to need the natural log of A, and there it is here, and we're going to need 1 over A, and those values are here. And so again, we'll prepare 3 plots in Excel. Plot 1 will be the natural log of A, or natural log of our NO2 versus time, to test to see if the reaction's first order, whether that's a straight line data or not. Our plot 2 will be 1 over the concentration of NO2 versus time to test for a second order. And plot 3 will be simply the concentration of NO2 versus time to test to see if the reaction is zero order in A. And again, we ask, which one, if any of these, will fit a linear relationship? Well, let's take a look. Remember, plot 1 is checking to see if the reaction's first order in A. So what we're going to do is plot the natural log of the reactant versus time, and this is the result. So the blue points here are our data points. The trend line is the red dotted line, and Excel gives us the equation of the line. That's the slope and the y-intercept. So we look at this line and we say, well, those points are not exactly on the line, and you have to ask yourself, well, is this red line a really good fit of the data? Or is there real curvature in the data, meaning it would not be a good fit? Or is this kind of curvature of the data points simply because there's some error in the analysis? Well, we can get some information by looking at the fit. We can also have Excel spit out this R squared, what's called a correlation coefficient. And if you recall, a good linear fit is indicated by an R square value very close to 1. Well, 0.9824 certainly is close to 1, but we might be able to do better. So our preliminary conclusion here is, let's withhold judgment until we see the second order plot. Well, Let's see the second order plot. Remember, a second order plot is 1 over the concentration of NO2 versus time. This looks different, of course, because we're plotting the data differently, but now the trend line is right on those data points. Here's the equation of the line. And it looks like the trend line, which is a linear trend line, is an excellent fit for the data. The R squared value is 1, which is perfect. Kind of hard to believe. It's an excellent correlation. So we're going to say the reaction appears to be second order in NO2. In other words, the rate law would be rate equals K times NO2 squared. Remember, again, what we're doing is we're finding a rate law without having to do the method of initial rates. We're using our expertise with integrated rate laws to find the rate law. Well, it appears to be second order, but for completeness, let's view the attempted zero order fit. So the zero order plot would be plotting just the concentration of NO2 with time, and you'll see this is a horrible fit. So here are the data points, here's the linear trend line, and you can see the correlation coefficient is quite low compared to even the first order plot. This is the worst of the three. So the reaction is definitely not zero order in NO2. So let's summarize. Remember, this is our reaction. It fits our profile. The first order plot was not bad, but we thought we could do better. The second order plot was beautiful. The zero order plot was horrible. And so we declare a winner, the second order plot. So we say, since this has the best linear fit, we conclude that the reaction is second order in NO2 and the rate law is rate equals K times NO2 squared. The integrated rate law, of course, would be of this form. We stated that previously. If this is the rate law, then that's the integrated rate law. Or if we cast this in the form of a straight line, it looks like this. And the reason, again, we point this out is because we're interested in the rate constant for this reaction. And the rate constant is simply the slope of this line, which would be 0.5431. And since this is a second order rate constant, it would be units of mole per second. And we simply read the number off the slope of this second order plot. So the complete graphically determined rate law would be rate equal, for this reaction, would be rate equals 0.5431 per mole per second times NO2 concentration squared.